Good evening to all colleagues. Welcome to the third day of the focus program. I share a PDF file for you. Let me go to the chat. Doesn't work. I should come back again. I don't see the chat anymore in my screen. Here it is. And I share the here it is, main chapter. This is the PDF file that exists by now, and I use it for these lectures, but I mean, for sure it will be modified, and the final version will be also available. To continue the last part, yesterday we saw some type of representation theorem. The whole strategy yesterday was to start on T. So recall F in LP of T or mu in M of T. These are given. So we are on the boundary. That was the first step. Then we use convolution. And we defined U as P convolved with F or U P convolved with mu. So now we have something on D. This lives on D. And then we studied the properties of this U. We showed that when we consider, this was the third one, U R, which means the restriction of U on the circle of radius R, in some sense, U goes to F or UR goes to mu. We saw it yesterday. Sometimes we have convergence in the norm. Sometimes we have weak or weak star convergence depending on which setting we are in. That was the whole thing we discussed today. Today, we do it the other way around. In other words, we start, instead of starting something on T, we start with something on D. So U is given, I say today. U is given on D. So we have no information of what's going on T. And now our goal is to show that there is something on T. Sometimes a function U, sometimes a measure mu. Something exists. And then explore the relation between this U and the little u, which is on the boundary, or mu. So it's the inverse operation of what we did yesterday. And then when you put these two together, you obtain a complete picture. Usually the theorems are given in this way. F is in HP if and only if. So one part is the if part, the other is the only if part, but I separated them to see what's going on. So to to obtain the final theorem, and we need to do this part. I mean, starting from the the recall yesterday we started with a simple case which gives a very strong result. I mean, continuous function. In a sense, it's the smallest space we considered. Then after the continuous function, we considered measure, LP, and finally L infinity, because in each step we needed the result from the previous step. We do the same here. We want to study functions on U. The first step, we start with the simplest and the most beautiful, the nicest case. And the nicest case is that U is defined on something bigger than the open unit disk. The notation I used here, I look at my other screen, notation. I used little h of d bar. Little h is for the harmonic, so it's the space of function u such that u is defined on a disk of radius r, defined on radius r, avec its value. It really doesn't matter if we consider real or complex, it's the same. Because even if we consider the complex, we can treat the real and imaginary part of it. But the important thing here is that that's the main essence. S is bigger than 1. And U harmonic. So we consider the harmonic function which lives on a disk bigger than the open unit disk. If we do this, this part becomes trivial. We do not need to say something exists on T, because the function is already defined on T in the best possible way. We have it on the boundary. And that is why we have this theorem, which is a bit different from the theorems come afterward. In all the coming theorem, there is always a phrase, it exists something. There exists a measure, there exists a function, but here you don't see there exists because it's already there. So let U be in holomorphic, harmonic D bar, HD bar, then immediately we have the representation we are looking for. U of r e to the I theta is what we expect, the Poisson integral, 1 over 2 pi, integral from 0 to pi, 1 minus r2 over 1 plus r2 minus 2r cos theta minus t. That's the convolution of P with what we already have. U of e to the it. That's already well defined, dt. Because that's the open unit disk. It is radius 1, and this is radius r. And our u lives here on something bigger. Therefore, on the point of unit circle, there is no problem. It's already defined. We don't need to say that something exists. And even though this is the special case and the proof is easy, we will see that in the upcoming theorem, we use this result to prove our representation theorem. There are several proofs for this. The one which is in the note is based on two things. First, since U is harmonic, we have a series representation. We showed this before, that U at r e to the I theta can be written as sum n from minus infinity to plus infinity an r to the absolute value of n e to the I n theta. We saw this before. For all r e to the I theta in dr. At all points here or inside, we have this representation by series, and the series converges uniformly on compact sets. Second, we have a formula for an, and the formula can be given by integral on any circle inside dr, in particular on the red one you see here. We can write 1 over 2 pi, integral 0 to pi, u e to the it e minus int dt for all n in z. So, but now, even though this formula is is valid for even r bigger than 1, we consider r less than 1, and we plug an here. And because r is less than 1, we can change the order of integral and the order of sum and obtain something interesting. Then u of r e to the I theta becomes the sum, and from 1 minus infinity to infinity, the coefficient 1 over 2 pi, we saw the coefficient 0 to pi u e to the it e to the minus nt dt. And then we had r to the exponent absolute value n e to the in theta. And the fact that r is less than 1 allows us to change the order of integral and sum. And see, this is equal to 1 over 2 pi, integral from 0 to pi. We take the sum inside. R to the absolute value of n e to the in theta minus t, and then u dt. We are almost done, because you remember the formula. I provided 2 formulas for P and 2 formulas for K, the Feyer kernel. One by series and the other, it shows that it's positive, and the other one shows its Fourier coefficient. One of the formulas we saw yesterday for the Poisson integral was precisely this one. This is precisely the formula for the Poisson kernel. It's PR e to the I theta minus t, u e to the it dt. And that's the end of proof. Even though you do not see complex analysis here, but it's hidden in the background. How do we prove this series representation? The most natural way to do it is to see that u is the real part of an analytic function. And for analytic function, you have Taylor series representation. You write the Taylor series representation, you take the real part, and you obtain this series. So even though you do not see at the first glance, the complex analysis is there. And even though it's not in the PDF file, we can be kind of more honest and give a proof in which you see the essence of complex analysis. Very rapidly, I say how it works. U is a real part of a function, call it big F, because our domain is simply connected. And in this domain, which contains the the open unit disk, you consider Z here and its reflection with respect to unit circle. If it's close to the boundary, the reflection is close, but if it's close to the origin, the reflection can be even very far, but it really doesn't matter. The point is that Z is inside. And then we have these formulas, F based on this integral over the unit circle. We can say that if we do the integral over T, F of zeta minus Z d zeta, 1 over 2 pi I, Cauchy formula tells us that this is equal to F at point Z. That's the, most important theorem in complex analysis, Cauchy integral formula. True, because Z is inside. But if you consider the reflection with respect to the unit circle, 1 over Z bar, then the integral over T, F of zeta minus 1 over Z bar dz, here 1 over 2 pi, for the value is not important. It's equal to 0, because again, that's the Cauchy integral formula. It stays outside of our domain. The domain here is disk, and on that, on the boundary, F is analytic, and 1 over Z bar is outside. Then formula 1, formula 2, and do 1 minus 2. The formula 1 minus formula 2. Still, you have a representation for F. But do the calculation. It's not difficult. And you'll see that after some calculation, you see that you obtain 1 over 2 pi, integral from 0 to 2 pi, precisely what we are looking for, the Poisson integral. F at point Z, or R e to the I theta. Z is R e to the I theta. If you do 1 minus 2, you precisely obtain the Poisson representation for the function F, and now take the real part of both sides. Here is the point that we use the fact that P is real valued. It's even positive, but being real valued is important. If you take the real part of both sides, you can replace F here by real part of F, and the same here. And note that it's 1 over 2 pi, it's not 2 pi I. I is already simplified. That's another way to prove the Poisson representation for the functions we consider, the functions we sleeve on a disk bigger than the open unit disk. It sounds to be a second proof, but if you look carefully and go into the detail of the proof, you'll see that this is not really different from the proof I provided here. The proof I provided here is essentially the same thing, except that I hide the Cauchy integral formula. But being honest, I'm doing this without mentioning the detail. I think Anatoly is laughing. Maybe you want to say something, Anatoly. You agree with that? Okay, so that's the first step. Good. And now, as I said, in the next step, we do not live on the boundary at the very beginning. We need to find it. And here is the first theorem, which is rather old, due to Fatou. Let u being h infinity of d. I did not define h infinity of d little h infinity, but it's clear from the definition. It's harmonic functions which are bounded on d. Then you see the difference here. Then there exists. That's part of the conclusion. There exists u in L infinity of t such that we have the same representation formula. U of r e to the I theta is 1 over 2 pi integral from 0 to pi pr e to the I theta minus t. And the little u that we found, dt. Okay, so inside the disk, big U, capital U is given. Somehow we get the function U on the boundary, and that's the connection between capital U and small u. How to do that? Now you see why, indeed, on Monday, I emphasize on the role of Riesz theorems for duality. The dual of LP is LQ, and the dual of C is M. Now we need them here. So the proof is based on two facts. First, L infinity is the dual of L1. L1 star is L infinity. I need this. And second, it's the fact that L1 is separable. I use these two facts to arrive at the conclusion. How do we do that? First, consider the function u, I call it n, u, an index n of z, defined by u of 1 minus 1 over n z. To avoid the problem with n equal to 1, we start with 2. Even for 1, it's okay. Why such a function? First, it really doesn't matter which sequence which goes to 1. Here I chose 1 minus 1 over n, but any sequence which goes to 1 from below, it's okay. 1 over 1 minus 1, 1 minus 1 over 2 to exponent n, it really doesn't matter. So we have a sequence which goes to 1. Why we did this? Because now un is defined on a disk of radius bigger than 1, on the disk of radius n over n minus 1. And n over n minus 1 is bigger than 1. We use the previous result now. Based on what we saw before, by the previous theorem, we can say that u index n at the point r e to the I theta is given by the Poisson integral pr e to the I theta minus t. And what do we have on the boundary? We have un on the unit circle dt. And un is 1 over 2 pi integral from 0 to pi PR e to the I theta minus t. It's u at 1 minus 1 over n e to the it dt. And on the left side, we have u 1 minus 1 over n r e to the I theta. Another way to interpret the same thing is that, well, the function is defined on the open unit disk. I went a little bit inside disk of radius 1 minus 1 over n. And here on this disk, everything is nice. I can write the Poisson integral, and this is precisely the Poisson integral I needed. True, but I mean, we can also change the scale and go to the setting we had before, and from here go to that. It's completely equivalent. Now, this is valid for n equal to 2, 3, 4, up to, I mean, grows, and let n goes to infinity. If n goes to infinity, on the left side, we have no problem. Function u is harmonic, therefore at least continuous. So we see that immediately this goes to u r exponent I theta, e to the I theta. No problem for that. But what happens on the right side? What happens on the right side? It's not clear at the first view. We have the limit of an integral, and well, as usual, we are willing here it is. If I erase this, when I take limit, when I put a limit here and a limit there, n goes to infinity, well, no problem on the left side. But here, I mean, as usual, we are willing to write that it's 1 over 2 pi integral from 0 to pi PR e to the I theta minus t times lim of u 1 minus 1 over n e to the it dt. But there is a problem here. What is this limit? At this moment, we have no information. Of course, later on, we will see that, yes, this limit exists almost everywhere and goes to the little function that we will find in a moment. But at the point, there is a serious question here. Why we can take this inside, and what is that limit? We do not have enough information. That is why we do a detour to answer this question. And the detour is like this. Consider, so now we do some calculation and operation to give a meaning to this definition. Consider lambda n defined on L1 with its value in C by the following formula. Lambda n of f is 1 over 2 pi integral from 0 to 2 pi f and u 1 minus 1 over n. N is fixed. E to the it dt. This is well defined. because this function is in L infinity, and this function is in L1. Remember the Risk theorem. This theorem says that this is a bounded linear function on L1. So lambda n is in L1 star. So this theorem. And also the norm of lambda n is equal to the norm of un in L infinity, which we know is less than or equal to the norm of u in H infinity, because the norm of u in H infinity is the supremum over the disk, while this is the supremum on a circle inside the disk. So of course this is less than that one. So you see lambda n, the important conclusion happens precisely here. The norm of lambda n as a functional is less than or equal to something which doesn't depend on n. This is valid for all n. So we have a linear functional, a sequence of linear functional, which is uniformly bounded. At this point, we have two possibilities. Either we use tools from function analysis and go very close to the end, and the tool is the Banach-Alaoglu theorem for the separable case. You say that we have a bounded sequence, so it has a subsequence which is convergent with respect to that topology. Immediately, we obtain the result we are looking for. But the way I explained in the text, I tried to avoid the Banach-Alaoglu theorem. But again, if you look at the proof and compare the proof of Banach-Alaoglu theorem for the separable case, you see that I repeated the proof of Banach-Alaoglu here because I didn't want to use that technical word. So from here, I said we have two options. We go for the longer option because it's easier to understand what's going on. And also we see the contour diagonal technique, which is the heart of analysis. So how to proceed? We saw that L1 is separable. Good. So we can find a sequence Fn, which is dense in Fn, dense in L1. And now what we can say about lambda n of just F1. Absolute value of this is less than or equal to norm of lambda n times norm of F1. This is in L1. This is as a functional. We saw that this is bounded, it's here, by the norm of u in H infinity times the norm of F in L1. Something fixed which doesn't depend on n. And this is a sequence of complex numbers. A sequence of complex numbers bounded, bolts on a Weierstrass, there is a subsequence which is convergent. And because we will have subsequence and then subsequence of this subsequence and so on, it is difficult to write indices. One way to do this, say that there is lambda n, I put it 1j, 1 because it's the first one, such that the limit of lambda n1j when j goes to infinity of F1 exists. This is 1. True. So we extracted a subsequence such that the subsequence is convergent at one point. The next step, we consider lambda n 1j, the same subsequence, but applied to F2. Applied to F2, it's not necessarily convergent, but as here, we know that absolute value of lambda n1j of F2 is bounded by the norm of lambda and the norm of F2, but the norm of lambda is uniformly bounded by the norm of U. Again, something bounded. And now we can extract a subsequence of this. A subsequence of this, so there exists lambda n 2j, such that lim j goes to infinity, lambda n 2j of F2 exists. And at the same time, note that since lambda 2j is a subsequence of lambda 1j, this limit also exists if I replace 1j by 2j. So this is important to keep in mind. But note that at the same time, lim j to infinity, lambda 2j, but applied to F1 also exists. And that's the way we proceed. So we had one sequence, we extracted something which is convergent at F1. Then from that subsequence, another one which converges at F2, we continue. And each time we go sub. At the end of the day, we have a sequence. So by induction, there is lambda, call it Kj, such that the limits j to infinity lambda Kj f k exist. And at the same time, because this is the subsequence of the previous ones, and lim j to infinity lambda Kj of f1 and lambda Kj of f2, Kj or nkj doesn't really matter. And up to lambda nkj of fk minus 1 also exists. So that is why we construct such a subsequence. And now this is the time to apply the contour diagonal technique. If I write it this way without n, we have lambda 1, 1, lambda 1, 2, lambda 1, 3. This is the first subsequence. The second one is lambda 2, 1, lambda 2, 2, lambda 2, 3 is a subsequence of the previous one. And we restrict ourselves to the diagonal. So you can see that lambda nkk or lambda kk is the same. K bigger than or equal to 1. By construction, lim, k goes to infinity, lambda kk of fn or exist for all n. Because, for example, why does it exist for F3? For F3, it is true that possibly lambda 1 is not here, or lambda 2 is not here. But from the third index, lambda 3 is the first element which is there. And lambda 4 is either this element or something afterward, because it's a subsequence. So from here downward is a subsequence of the third line. And that is why lambda kk of F3 also exists. That's the essence of contour diagonal technique. And now we can go more than that. We can go more than that and claim, in fact, lim k goes to infinity, lambda kk of f exists for all k, for all f in L1, not just the sequence we can see. And here is the point that separability comes into picture. What we did up to here works for any sequence. You choose sequence Fn, and from your lambda k, you choose another subsequence which converges for F1, for F2, for F3. Nothing about the structure of L1 as used. Now we use the fact that these Fs, F1, F2, F2, are dense in the L1. So given F, given F in L1, and even you can fix epsilon, we want to show that lambda kk of F has a limit. So what can we say about lambda kk of F minus lambda k n, well, lambda, say LL of F. I want to show that it's a Cauchy sequence. What can I say about this? What is the upper bound of this? The same technique that I mentioned even yesterday. I write F equal to F minus Fn plus Fn. It's something ridiculous, childish, but that's the point. I mean, this gives us the answer. And the fact that lambda kk are uniformly bounded. So if we apply this, I mean, identity and put it there, we see that lambda kk of F minus lambda LL of F is less than or equal. Three things. Lambda kk of F minus Fn plus lambda LL of F minus Fn, and finally lambda kk of Fn minus lambda LL of Fn. The important thing here is that lambda kk is uniformly bounded, so I can get rid of this and this in the next step. So it's less than or equal to the norm of u in H infinity times norm of F minus Fn in L1 for this one and for this one, so twice. So there is no presence of K or L here. And the other one I just repeat. Lambda kk Fn minus lambda LL Fn. Now I choose my n such that say this combination is less than epsilon, or if you are willing to arrive at epsilon at the end, you can put this epsilon over 2. Really doesn't matter. So choose n such that this is less than epsilon. And we succeeded here again because this quantity doesn't depend on K or doesn't depend on L. So we can put the whole thing here less than epsilon. Now N is fixed. So I repeat the other sentence here, put it here precisely as it is. N is fixed now. And N is fixed, we know that lambda kk is convergent at F1, at F2, at F3, as any one of them. Now we choose K and L big enough. Next step, choose K and L large enough, such that this is less than epsilon plus epsilon, and we are done. So again, I went into detail here to show how can here it is. I went into detail here to show how can extract from this lambda n a subsequence which is convergent point-wise at all points. Everything is mentioned here is in fact the proof of Banach-Alaoglu theorem in the separable case. But I went into detail to show what's going on. And why I did all of this. The reason is that I can choose a special function. Recall the definition of lambda. Okay, now that the limit exists, no, we know that now. We know that lim k goes to infinity, lambda kk of f exists for all f in L1. This allows us to define lambda by this formula. So lambda of f definition is equal to this limit. And since lambda kk of f is less than or equal to norm of lambda kk, norm of f, and norm of lambda kk is bounded by the norm of u in H infinity, then we conclude that lambda f is also bounded by the norm of u times norm of f. So it's a bounded linear functional. So lambda is in L1 star. And the Riesz theorem tells us it's again Riesz theorem. This is L infinity. And that's the point that the magic happens. So Riesz tells us that there is a little u1. Now we find our u1 after so much calculation, so many lines of precision. Now we see where it comes into picture. Riesz tells us that there is u in L infinity such that lambda f is equal to 1 over 2 pi integral from 0 to pi f, no r, e to the it u e to the it dt for any f in L1. So this is the point that we overhand on something we were looking for. And note that U is initially defined by this formula. I'm gonna use that. Even, how do we use that? We are allowed to put any function we want here. And in particular, fixing Z, I consider the following function, f e to the it equal to the Poisson, PR e to the I theta minus t. Note that R and theta are fixed. Even I can even put a small z here so that z acts as a parameter here. So what do I obtain if I consider this function? On one hand, lambda of f of z is given by this formula. So it's 1 over 2 pi integral from 0 to pi PR e to the I theta minus t. The u that was given to us by Riss dt. This is a consequence of this formula. And what would be the consequence of the other formula? On the other hand, we know that also lambda f of z is the limit k goes to infinity lambda kk of f of z. And lambda kk f of z, by the definition of lambda k, is the limit k goes to infinity 1 over 2 pi integral from 0 to pi PR e to the I theta minus t. And u kk e to the it dt. And we saw, I mean, this is our first theorem that we saw today, Theorem 1. That is why in the first case, we went to a disk larger than the open unit disk. Our first theorem says that forget about the limit. The whole integral here is u at the point 1 minus 1 over nkk r to the I theta. Even at some point I mentioned this theorem, it should be available up there. I remember I wrote it. Here it is. That's the theorem we saw above. And therefore, we are done. This is precisely u of r e to the I theta. And that's the end of the story. And note that this is precisely the formula that we are looking for. On one hand, lambda f of z is equal to the u, as on the other hand equals to this. So conclusion, therefore, u at the point r e to the I theta. I mean, I simply write PR composed with little u at the point e to the I theta. This is the integral we had before. And also in the proof, we saw that the norm of big U in the proof also we saw that. The norm of U as an element of H infinity is equal to the norm of the lambda as a function on L1, as an L1 to C, and this is equal to the norm of U as element of L infinity by Riesz theorem. Well, that finishes the proof for the case H infinity, little h infinity. I went into detail to explain what's going on, but I mean, we take a break now, and after the break, we mention the other theorems, but I mean, it will be a sketch of proof and see what's going on. Thank you. So it's 10:56. We can come back around 11:05. Someone asked, is there a shorter proof? As I said, yes, there is a shorter proof, but you need to use heavy tools. Pretty much 70-75% of this proof can be removed and replaced by the word by the Banach-Alaoglu theorem. So if you know what is the Banach-Alaoglu theorem, you can, yes, from here, precisely from here, when we show that the lambda n is uniformly bounded, from here up to the rest, up to here, it's not needed. We can immediately say that, so there is a subsequence which is convergent and go for the rest. So a lot of details can be avoided and hide behind the wording Banach-Alaoglu separable case. I went into detail to show what's going on. And since some people came later, well, there was a PDF file which I shared, but if you come later, you do not see it. Please allow me to share it again. That's not the final version, and that is why we do not put it on the website, but still it can be useful for you. It will be modified a bit later on, and the final version will be available. Very question by Saika. Is U, no, U is unique. And the reason is another theorem of Fatou. You're right, I use a sequence. Somebody else can sequence 1 minus 1 over n. Someone else can use another sequence. So there is no reason that we recover the same U. So from what it's said up to now, it can be different U, but no, it's unique. And the reason is the theorem of Fatou. After the break, I will mention that there is another relation, more difficult to prove, between capital U and little u. Thank you for this interesting question. Manders as this function U that we get in a... okay, it's the same question. It is unique. I will answer after the break.